Yeah, thanks, Ray. Thanks, Scott, and thank you, everyone. So my talk today is called "Don't Be Outflanked," and for those of you, obviously in the industry, you know that flanking is a term which we generally associate with sound transfer through construction gaps. I'd like to extend that a little bit today to talk about gaps and cracks in general, and also the effect of those gaps and cracks on air leakage. So to do that, I guess what we're going to do is start off in a historical position. These two houses, I Googled when we did the presentation, I Googled the most expensive suburbs in Australia, and Mossman in New South Wales and Toorak in Victoria came up. And these sort of houses you would assume would be of the time, of the era, master built, had architectural design in them, so they were probably the leading houses of that era. These houses absolutely were designed on maximum or sort of a significant amount of uncontrolled ventilation. So what that means is that there were gaps and cracks in walls and around doors and openings, and which actually was promoted. There were vents in walls, and these vents allowed smoke to egress because they used kerosene lanterns in the old days before electricity, and they used smoke fireplaces to warm the houses. As Scott said, they would have been zoned off into tiny little spaces, so you would have only heated a very small component of the house, and the rest of it would have been unheated. And things like your kitchens and bathrooms, the wet areas, the laundries, those sort of areas, typically were sort of at the back of the house, disconnected from the living spaces. It was very much the old era. Those areas were at the back of the house, and this is significant because today what we actually see is things like the kitchen is the heart of the house. It's absolutely right in the middle of the living, dining and entertaining space. And of course that area is an area that creates a lot of moisture, and you're probably going to hear a little bit about that in Jesse's presentation later on. So I think to have a look at the sort of uncontrolled ventilation, and I like to differentiate that from controlled ventilation, because controlled ventilation is windows and mechanical ventilation. We open a window, we can control it, we can turn on mechanical ventilation and turn it off again. That's controlled ventilation, but gaps and cracks in buildings are uncontrolled ventilation. We cannot turn them on and we cannot turn them off. Some examples of these, obviously, I'm just going to show you very quickly on the slides. This is a thermal image camera, and down on the right-hand side here you'll see a range, and this range varies from every slide between a minimum temperature and a maximum temperature. The minimum temperature is the dark purpley colour, and the maximum temperature, of course, is the more yellow colour. So what we're looking at on the first image here is an area around an old cypress pine floor. We've got a vent in the floor here, and what you can see under the thermal image is you can actually see air coming up through the gaps in the floorboards. And this is about a 4-degree temperature change. So this is absolutely uncontrolled ventilation. On the other side, what we actually are looking at is the gap underneath the sill of an external door. And in this case, what you can see is that's about 8 degrees cooler than the rest of the house. So this is, a significant temperature difference. And for people that have lived in older houses, you would definitely have felt these sort of, the effect of that airflow. Of course, we also have, in a lot of houses, ducted heating systems. Now, what you can see in this slide is you can see the warmth around the ducted flooring heating system. But of course, what we can see is around the skirting board, again, a significant cool draft around there. And of course, this is a fixed wall vent. Quite obviously, you're going to get air coming in and out of that wall vent. It's the purpose of the wall vent. So, this is all uncontrolled ventilation. That uncontrolled ventilation was actually promoted. And as I said before, it was promoted for a number of reasons. In the early days, before electricity, when we had kerosene lanterns, it was to take out the kerosene fumes. It was to take out the smoke from open fires and to take the water vapour out from, your cooking and bathing. And this is very critical today. The water vapour that is generated in a house through breathing, cooking, drying clothes inside in cool climates, which is a common thing that we do, that vapour's got to be dealt with somehow. Jesse's going to handle a lot of that later on, but it's very critical. It's critical because, the National Research Council here has suggested that about 90% of our time is now spent indoors. The gaps in houses, historically, about 39% of those, 39% of the air leakage was through the wall vents, and 13% was through around unsealed doors. As Ray suggested, we design buildings on a pure essence of trying to minimise active heating and cooling, but in reality we know that people go and put air conditioning systems in and they use that regularly. So there's a big disconnection between the way we know houses are designed and the way they're actually used. And you know, this is all about comfort. You know, people want to have that idea of absolute and total comfort. They rely on that for heating, ventilation, for cooling the house in summer, obviously. You know, this leads to significant increase in energy consumption, costs associated with energy consumption. And as I said, you know, 90% of our time is now spent indoors, whether it's in our own homes or in our workplaces. So the indoor air quality is critical to us. Probably there's a link there, of course, that now about 10.2% of people suffer from asthma, which is a respiratory-based disease. So, you know, while we're spending more time indoors in sort of white-collar type employment, we're also suffering from asthma. We know that there's a desire for improved health of occupants. You know that anecdotally because we spend millions and millions and millions of dollars on vitamins, you know, which is to sort of make us feel better. Some obviously do probably a better job than others, but also what we just heard recently, and this is important because we didn't know this up until, you know, actually a couple of months ago, is that now there's a medical link. There's a medical link between comfort and mortality, and what that link is saying is that when we for those people that are exposed to prolonged cool periods. So that's not just, you know, hours and hours, but that's day on day living in one of these leaky tent houses. There is a negative side effect, and that is that we suffer from higher blood pressure, and that was identified in the medical report that Ray alluded to at the beginning of the talk. And this is something that we've only just really recognised. So now we actually have. It's not just about comfort, but we know it's also about a health outcome as well. Now, the building code talks about sealing of buildings. It talks about it in both Volume 1 and Volume 2, and it's, you know, in Part J3 of Volume 1, it talks about it's applied to elements forming the envelope of the building. So that's the external envelope of the building. Has a number of exclusions, and those exclusions are around in certain climate zones, typically warmer climate zones are 1, 2, 3 and 5, where for air conditioning you'll use evaporative cooling. They allow the building to be leaky. Where you may have a unflued gas heater, I know that in Victoria you're not allowed to, but where you may have that for a health outcome, they allow also the building to be leaky as well, so that the toxic gases can exit the building through all those leaks. And in a larger building where you've got a mechanical ventilation system, you know, which is a pressurised system, it also allows the building to be leaky as well. But the building code is a performance-based code, right? So it's really important to go and have a look at the language around the performance components of the code. And again, in Part J3 of Volume 1, it talks about constructed to minimise air leakage. It talks about things like internal lining systems that are close fitting at ceiling, wall and floor junctions. It also talks about sealed by caulking of the skirtings, architraves and cornices. So, you know, I don't know how you would interpret this, but I don't actually suggest that that's really a performance criteria. I mean, obviously it doesn't say maximise air leakage, it says minimise air leakage, but it doesn't actually say, you know, set a datum of what type of air leakage or what the number of air changes within the building, you know, we should be targeting. If we go and have a look at Volume 2, very similar. It also in Part 3, 12.3, building sealing, it talks about it's applicable to, of course, Class 1 and Class 10A condition spaces. It has a number of exclusions. Again, it excludes climate zones 1, 2, 3 and 5 when you're using an evaporative cooler. Again, it excludes areas that require ventilation for gas appliances. And it also excludes Class 10A when you've got accommodation of vehicles. So that's, of course, a garage. Interestingly, of course, the garage is the area in a building, in a house, that we know most pollutants actually enter the building through. And the reason that is because, you know, most of us will have a garage door and an enclosed garage, and we have a door that links the garage back into the house. And, You know, what we'll do is we will get into the car in the morning. It's pretty cold, so we leave the garage door shut. We turn over start the car up to warm it up, and then we realise we left our mobile phone inside, so we duck off inside, leave that door open, hunt around the house for a couple of minutes to find the phone, come back to the garage. But by that time, in that enclosed space, the car's pumping out a lot of carbon monoxide. That carbon monoxide enters into the house, so that is a point of, you know, the worst point of pollutants entering the average house. It has exactly the same language again. It talks about minimising air leakage, close fitting of your internal lining at ceilings, walls, floors, junctions, and sealed by caulking for skirtings, cornices, architraves and the like. Again, this is performance. I think that's questionable whether that is actually performance or not. And I'd say that as an architect, you know, an architect practicing in New South Wales, I've actually never seen any of that done. I've never seen your internal layers sealed, and I've never seen sealing around skirtings and architraves. Probably there is a bit of sealing around cornices because we tend to install cornices with cornice cement, and that just the method in which it's applied to, it tends to seal that joint. But apart from that, I really don't see a lot of sealing happening in buildings. So I guess one way to look at this is actually to actually measure the house, and of course Ray suggested we have the CSR house, and that's a great living laboratory. So what we did is we used a blower door fan pressurisation test. You can see the image of the unit on the right hand side. That's in the doorway between the garage and the rest of the house. You put it into the doorway, seal it up, and then you operate the system, and it sucks air out of the building and measures the air leakage at 50 pascals. The reported, the data you get from that is a figure of ACH, air changes per hour over 50 pascals. And so that's a measured temperature, that's not an ambient temperature, that's not a real figure. So what we do, and I've given you the basic formula, if you want to compare a measured formula to an ambient figure, you divide that ACH 50 over 20. So in this case, a very simple formula. If we have a 20 ACH 50, we divide it by 20, we'll get an ambient air changes per hour of about 1. So that would mean the total air volume of that house is actually exchanged every hour. Obviously, air leakage can occur through a lot of different parts of the building. It can go through the subfloor. It can go up old chimneys if there are, you know, the old the fuel wood burn stove. It can go through the gaps around doors and windows, through your vents, you know, in your bathrooms, through your air handling units, up into the ceiling. You know, there's numerous ways that you lose air out of the building as long as they're not sealed. If we just look at this really diagrammatically, because we like these sort of things, that, you know, if we replace all the air in that house once per hour, you know, that's a significant amount of heat and energy that's therefore being removed out of the house. If we just slow it down by half, so we remove the air, the total volume of the air, we change that every 2 hours, it's going to be a significant improvement, you would think. How do we measure up? It's important we have a look at how we measure up. In American European building codes, the target for an ACH 50 is between 2 and 3. The passive house, which is a zero carbon house, a very low energy house, German house is a 0.6 ACH 50. And the CSRO did a number of testing of existing Australian houses to identify what the air changes per hour is, and they came up with an ACH 50 of 19.9. So as you can see, you know, we're nearly 10 times the American and European standards. We're 50 times the passive house standard. I mean, that means, you know, it absolutely supports the statement in the medical journals that, you know, we're building very leaky buildings, and they're probably no better than a tent. Obviously, as I said, every hour, if you're going to replace all the air inside your house, you're going to reheat that or recool that, because we know from Ray's slide on comfort, the period in a year where we actually achieve that comfort level of about 22 degrees is very, very small. So we're doing a lot of heating and a lot of cooling during the year. And if we've got to do that every hour, we're just, you know, churning up a lot of energy and a lot of wasted energy. We always like comparing ourselves with the New Zealanders. You know, it's an Anzac tradition, isn't it? And this chart looks at the air changes per hour. The black is of course New Zealand. The green and gold, of course, is Australia. And you know, the New Zealanders have been actually measuring this for some time. They started measuring it. Brands released a report in 2012. And what this, just to give you an idea, this is the age of the building that they've been testing, and this is the ACH 50. So here, if we look at ACH 50, that tested figure of about 20, that's a point where we, at an ambient level, we're replacing all the air inside that house every hour. So as you can see, back in the 1950s, the New Zealand houses were about where we are today. They've made some significant reductions over time. And now, you know, Brands did a report of more recently built buildings built in the 2000s, and the ACH 50 is less than 5. Very, you know, it's not quite as good as the European and American standard, but it's getting very close to it. Of course, you know, the next thing to consider is that those of you that have familiarity with the leaky building syndrome in New Zealand, you know, at around about that figure of 5, well, you know, they had dramatic problems with moisture build-up in buildings. So whether that's the catalyst or not, that may very well be. And what it really means that we should consider is that let's not just take, because it's done in New Zealand, let's not take that as a figure that we should adopt here. Let's go and do some further analysis of that. Again, in Australia, this is just charting again the age of the house from 1999 to 2010. And again, this is the air changes per hour. So the ACH at 50, so that's that datum level again. So what you can see is, of course, over time, we know we're making significant progress, right? You know, we're reducing substantially how leaky our buildings are compared to the buildings built even 25 years ago. But if we compare this internationally, you know, we're 30 years behind the Netherlands and the UK, and we're a long way away behind Canada and Sweden. You know, so this suggests that we've got a lot of work to do here. Of course, in Canada and Sweden, you're also talking about extremely cool climates, and you know, that may again be going too far. And in very cool climates, what they tend to do is seal both the inside and the outside layer of the external wall. You know, that would be probably a significant move away from the way we build today in Australia, and of course it has other effects on, you know, on weather tightening and how you handle water coming in from the outside of the building. Now this is again the data collected from the CSR house, and what you have is on the lower side here we have the air leak, you know, the leakiness of the building. So the ACH 50 at this at the lower level, and this is the ambient figure. So again, we have that datum point of about 20 ACH 50, which is one air change per hour. And on the vertical axis, what we have is the megajoule, the energy consumed to condition the floor area of the building. So what you can see is, as we make the building more airtight, in terms of our heating load, we significantly reduce the heating load on the building. So the amount of energy used to heat that building drops significantly. In terms of cooling, we also get a reduction, but it's less. Okay, and that's a typical assumption, ratio. What we also looked at in this is, and what you can see in the blue figure, the blue area here, is that this is around about 9.3 on that outside edge. That's the ACH 50 that the CSR house was tested at construction, at the end of construction. And then some modifications were made. I'll go through those in a minute. And that brought the figure down to around about 6.5. So just doing some additional post-construction modifications. Just interestingly, I think you mentioned previously the connection between the leakiness of the building and the modelling tool and the star rating. What we can see here is this is a what would you call it? It's not a pure model because there's some assumptions made in the modelling tool that the buildings are already going to be airtight, which we know they aren't. But what we know is that as we make the building more airtight, we can get a theoretical improvement in the energy rating of the building. And just to clarify that line there, which is around about 4.3, was the energy rating of the building under testing when modelled through Accurate. So there's a significant difference between what we tested at and what we actually achieved, and that concludes to what Scott said previously. What we get in reality is not what we actually modelled. Is that clear? Is that clear for everybody? Good. Okay, so where do buildings leak? We can predominantly say that this is a report or a book, a manual based on 1986, looking at a historical study. It was really based on three areas: smoke control. So a lot of buildings up until the 90s actually still required wall vents to remove smoke out of the buildings. It was mandatory. In some areas, it was mandatory to maintain four vents in the living areas of the house. So we know that the smoke control was one area. We know that the leaks around the building fabric, so that was skirtings and floorings and those sort of things, another area. So that's the construction. And we know that windows and doors is another significant area of heat loss. So as you can see here, wall vents accounted to 39% of the heat of the air leakage in these days. Probably some other figures: windows and architraves 29%, unsealed doors 13%, skirtings 11%. So it gives you a pretty good idea as to where we should be targeting if we want to make the buildings a little bit more airtight. In 2011, this was another study was done on exactly this, and really what you saw is the historic figure on smoke control now actually is now being we get similar sort of air loss through the mechanical systems and the HVAC system. So the duct work, the vents in the bathroom vents, the vents in the range hoods in our kitchens, and of course the ducts for our air conditioning, which are typically undampened. So now what we're seeing is the joints between the walls and floorings and ceiling. We get about 35% of our heat loss, our air leakage through there. Again, the cooling, heating, HVAC systems, flues, we've got a considerable amount of area there, about 35% of air leakage in there. Windows and doors still contribute 15%, even though they should be better built in this day and age. But this gives us a pretty good idea as to if we want to take a house and we want to control the ventilation better, we want to get rid of the uncontrolled ventilation, this is a pretty good indicator of where we should start. So this, of course, gave us the idea of what to do post-construction for the CSR house. So in this case, we used the fan blower test. As you can see, the unit we described in the doorway. This is the base building at completion of construction. We achieved an ACH 50 of just over 9, about 9.3 at that time. We then looked at a couple of modifications. And we looked at, so the first thing we did was sealed up anything to do with the air conditioning system. So the return air grills and the supply grills. So we taped those up. What this does is replicates the fact that we put in good quality dampeners into the HVAC system, into the air conditioning system. So rather than just uncontrolled air flowing in and out of the ducts, we've actually put a dampener in there to control that air. And that gives you a substantial increase. So we're down around the ACH 50 of about 7.5. We then looked at the next level, which was sealing the bathroom vents. So this is, the vents, of course, the extraction fans in the bathrooms. What this again would simulate is the same thing, that you're venting it to outside and you're putting a dampener in the duct as well. And we got an incremental benefit. Of course, the ducts in bathrooms are pretty small in comparison to the HVAC system. There's only two small rooms, being two small bathrooms. If you had multiple bathrooms, you'd have a bigger effect here. And the next area we looked at was all the other construction gaps. So in this case, we looked at, you saw these images previously in Scott's presentation. So this is the drafts around the architraves of the sliding doors. So we sealed up those gaps. We then sealed up the gaps where we had abutment of different types of materials. So in this case, we had, a masonry wall and a plasterboard wall abutting each other. That gap is always, difficult to seal unless you specifically go there and seal it. So we sealed up that gap. And the next thing we did was sealed up power points, manholes, front door gaps. So we obviously, put covers over the back of, in this case we just taped over the front of the GPOs. But what that would simulate is us putting actually, a proprietary fitting over the back of the GPO to minimise air leakage. And again, what we got was a significant reduction. So what you can see here is from the tested figure. So what this suggests is that at an ambient ACH of 0.46, we're replacing the total air volume in that house every 2 hours. So that's as per the end of construction. And when we did some further modifications, we basically brought that down to replacing the air within that house every 3 hours. So obviously that's going to be an improvement in the thermal performance. We're going to have a better internal environment. It should be thermally stable because we've minimised the uncontrolled ventilation. I guess it's important, on the basis that we don't really have a matrix in the building code. It just says minimise air leakage. So let's just, have a quick look at where we stand. Under CSRO testing, we know that we had a ACH 50 of about 19.9. The CSR house model and accurate came in at 4.2. We know that's unachievable in reality because as tested on construction it was 9.3. In rectified it was 6.5. And then we have the European standards of, between sort of 0.6 and 5. These are very high standards, and with probably some substantial changes in the way we build buildings, that would mean that we'd have to make an incremental, improvement in the way, or a significant improvement in the way we build to the way we build currently. We have done some testing of what you would call, let's call it targeted sustainable project home buildings, and they came in at around about the ACH 50 of 10. That was without anything significant. It was just good quality construction targeted at a more sustainable, customer base. It's really important that when we look at making the building airtight, that we also look at the ventilation as well. And the University of California in Berkeley did some studies on this. And this is because, quite obviously, if we make the building completely airtight, so if we went to the standard of a passive house of 0.6, so we're replacing the air in that building every 20 odd hours, right? I mean, it's obviously going to get potentially stuffy in there. You're going to need to control the air inside that building, because if 50 of us entered into the house today, we're all breathing away, we'd be consuming the oxygen in that building very quickly, pumping out carbon monoxide, and it probably wouldn't be a great party. So this strategy looked at this report looked at ventilation strategies. I'm going to start from the bottom. So again, on the right-hand side of this slide, we're looking at the ACH 50, the tested figure at 50 pascals, and at a figure of 27, which is where Australia was in the 1950s. These buildings are there's so much exchange of air that we don't need to do anything in our ventilation system. So we don't need to add air, we don't need to extract air, because the building's got so many leaks that the air is naturally doing that on its own. As we move up through the system, we start to get, say, at about, let's say if we go up to 20, which is where we are now under the CSRO report, is about 19.9, so pretty much where we are now. Again, we don't need to do anything. The buildings are leaky. It's like living in a tent. We don't really need to do anything. If we go to the extreme level, we go up to sort of, the 1, what we're doing then is we're making that building so airtight that now what we need to do is to balance air coming in and out of that building. So we need to monitor the indoor air quality, and we need to either extract air out of the building or bring air into the building to ensure that the indoor air quality is maintained. We don't want to build up a carbon monoxide, so we want to pump that stale air out of the building, and if we want to bring fresh air back into the building. So that's a really common solution in Europe, but quite expensive, and you definitely wouldn't be getting that in a standard house in Australia. If we move to, say, 5, an ACH of 5, we look 5 to 7, we're looking at a balanced or unbalanced system, or a totally unbalanced system. What that really means is that you don't need to go to the complex level of having a system which is monitoring air quality and bringing in air when it needs to and bringing out air when it needs to. You can just bring air in or out if you pump air into the building, there's going to be adequate gaps in that building that the stale air is going to be, due to air pressure, is going to be forced out of the building already. Okay, so that's really just, a ventilation system like an Edmund system, the Odyssey system, right? Very simple, cost-effective, things that we put in now. Whirlybirds would also do that as well, whirlybird on a roof. So not going to any extreme. So that level of around about ACH 50 of 7 to 10 looks quite good. We don't need to do anything fancy in terms of ventilation, but we know we're going to get some improvements in the efficiency of the uncontrolled ventilation. We're going to remove that uncontrolled ventilation. So I guess on this basis, what we've got to do is we're going to propose a figure here, and that figure is going to be on the basis that if we do what the building code requires us to do, we seal the internal layer of the external wall. We pay attention to things like, we also deal with the joints at the skirtings and architraves and the ceiling junction. We just look at good quality construction, seal construction gaps, put on dampeners in our ventilation system. So whether it be an HVAC system or a heating, cooling, or just a ventilation system, we put dampeners on our extraction systems. We make sure that things like the range hood above our cooktops are actually taking air outside, and you'd have a dampener on that. An ACH 50 of about between 7 and 10 is very achievable. Okay, so we get that balance between not having to, take everybody to a completely different planet in the way we construct, but just do things a little bit better. So we know that, by sealing the building and dealing with air leakage, we're going to reduce the drafts, right? Because we're going to reduce the uncontrolled ventilation. There's the drafts under doors and between floorboards and those sort of things are gone. That means that the internal air is thermally stable. We can control that. We've spent some time in dealing with thermal mass and placement of windows and buying the correct glazing, so we can keep a more thermally stable indoor environment. We've got a better indoor air quality as well, because again we can control it. And of course, it comes right back to the beginning in terms of flanking. We know we're going to get better acoustics as well. And we have a look at this chart. This is from a book from 2014, and what we look at here is transmission loss without leak along the horizontal axis, on the vertical axis, transmission loss with leak. And if we look at here, if we take 0.01% of the total surface area, so if we have leaks in our buildings or a gap in our building of around about that, so what that suggests is if we had a wall that's 2.5 metres high and 4 metres wide, 10 square metres, if we had a 1 millimetre gap along the entire skirting of that wall, that would equate to about a 0.01% gap. And what this is telling us is that where we targeted a 60 dB, that gap means that we have a 20 dB loss in acoustic performance, and we are only going to achieve a 40 dB wall. So just diagrammatically to look at this, what this would suggest is if you've got an insulated, relatively well-performing brick veneer wall, which achieves an RW of 60, and we don't handle all those gaps, so we allow there to be that high level of uncontrolled ventilation. We don't look at sealing all the gaps, around the walls, floors, around the windows and doors. What we're actually paying for is a single skin wall, single skin lightweight wall, which achieves an RW of 40. If we look at it like that, it's pretty obvious that we're just wasting money, right? And these are really simple measures. How do we do this? Very, very pragmatically, very, very simple. We make sure that our insulation is fitted tight between the studs. We make sure that it's installed properly, because we know now that we're going to get better thermal performance. We're also going to get better acoustic performance, and we have less transfer of air through those gaps. We go and look at something as simple as where you have a double stud in an intersection of a corner, we fill that with insulation. We go in at the bottom plate, we seal that with caulking. This is very simple. And we make sure that and of course your Your building membrane, of course, should be wrapped tightly and seal off around window openings and door openings. And we make sure that these little gaps that we identified before, particularly around skirtings and architraves, are actually sealed. We also make sure that, the seals, the gap between the door and the frames, or windows and frames, are actually sealed. And as I said, that the building membrane is actually properly wrapped around into the frame of your window and door openings and sealed and taped off. This is really simple stuff, right? We don't have to do anything. It's nothing major. It's just doing things a little bit better than what we currently do. So if we do that, we know we're going to get better air tightness. We know air tightness gives us better acoustics. We know that gives us better comfort. And this gives us this total better feel that Ray alluded to, that idea that the building just feels better than it did before. So what I would leave you with a takeout message is some sort of QA process. Comfort's a great selling point. It's an indicator of quality design and construction. And I'd say that in terms of, if you've ever gone and bought a house and you want to buy a house on a main road, and if you sit inside that house or stand inside that house or unit, and if you can hear the traffic whizzing by the road, in your mind you're saying, well, this can't be a very well built house because I can hear what's happening outside. If you walk into a similar house or unit, in the same circumstances and you can't hear it, we all in our mind say, well, this must be better because I'm sitting in here, I can see the noise outside, I know I can't hear it, so it must be better. I mean, I've gone to many houses and said exactly that, and I think a lot of people do when they go and buy houses. Consider a post-construction building test using the fan blower test. These sort of tests are only about $500 to undertake. They're not very expensive. And what you may find is that, you may find that you don't get the total improvement in the first house. So you put it inside a house, you do some testing, you may not get this, absolute perfect result from day one, but what it allows you to do is to put into place some measures, as you move forward to actually continually improve and test it again. Look at that ACH 50, that target figure of between 7 and 10. And from our point of view, we believe that this is a market-leading innovation, very, very simple to achieve, very cost-effective, and leads to better quality buildings. So again, we know, better comfort is going to come with better control. Control ventilation. Let us only have ventilation when we open windows and turn on a mechanical ventilation system. And if we do that, what we can achieve is a better quality of lifestyle without significant waste. So that's the end of my talk. Thank you very much. I'd invite some questions.